Think about a stack of plates. You add a plate to the top, and when you need one, you take it from the top too. So the last plate you put down is the first one you pick up. Now think about a line at a counter. The first person to arrive is the first one served. These two everyday patterns are exactly the two data structures we are covering today, the stack and the queue. A stack is a collection where you only ever touch one end, called the top. It follows a simple rule: last in, first out, or LIFO. The most recently added item is always the first one to come out. There are really just three operations: push to add an item on top, pop to remove the top item, and peek to look at the top item without removing it. Pushing adds an item to the top of the stack. The new item sits above everything already there, and the top marker moves up to point at it. Because you are always working at the same end, there is no shifting and no searching. Pushing is constant time, O of 1. Popping removes the item currently on top, the one you added most recently, and hands it back to you. The top marker drops down to the next item. Again, you only touch the top, so popping is also O of 1. Notice you can never pull something out of the middle of a stack. You must pop items off the top one at a time. Sometimes you just want to know what is on top without taking it off. That is peek. It returns the top item but leaves the stack exactly as it was. Like the others, it is O of 1. Push, pop, and peek. Three constant time operations, all at the same end. A stack is not a brand new kind of memory. It is built on something you already know. You can back it with a dynamic array, pushing and popping at the end, which we saw is amortized O of 1. Or you can back it with a linked list, pushing and popping at the head, which is always O of 1. Either way, because every operation happens at a single end, a stack is fast and simple. Two things to watch for. Popping from an empty stack is an error called underflow, and on a stack with a fixed capacity, pushing past the limit is overflow. This is more than trivia. Every running program uses a call stack, where each function call pushes a frame and each return pops one. If a recursion goes too deep and never stops, those frames pile up until you get the famous stack overflow. Stacks show up anywhere you need most recent first behavior. The undo feature in your editor is a stack of actions. The browser back button is a stack of pages. Checking that brackets in code are balanced uses a stack. And depth first search, which we will meet in graph videos, is a stack at heart. Whenever the rule is, handle the most recent thing first. Think stack. A queue is the opposite idea. It has two ends, the back where items join and the front where they leave. And it follows the rule first in, first out, or FIFO, exactly like a fair line of people. Its operations are Enqueue to add an item at the back, Deque to remove the item at the front, and peek to look at the front without removing it. Enqueuing adds a new item at the back of the queue, behind everyone already waiting. The back marker moves to the new item and the front stays exactly where it was. With the right design, this is O of 1. Dequeuing removes the item at the front, the one that has been waiting longest, and the front marker advances to the next in line. The oldest item always leaves first. The key question is how to do this without disturbing everyone else, and that depends on how the queue is built. Here is the trap. If you build a queue on a plain array and treat index 0 as the front, then every time you dequeue, all the remaining elements have to shift one step to the left to fill the gap, and that is O of n on every single dequeue. A linked list with head and tail pointers avoids this completely, giving O of 1 at both ends. But there is also a clever array-based fix. That fix is the circular buffer, or ring. Instead of shifting anything, you keep two pointers, one for the front and one for the rear, and you simply move them forward as you enqueue and dequeue. When a pointer reaches the end of the array, it wraps back around to the beginning, reusing the freed slots. Nothing ever shifts, so both Enqueue and Deque stay O of 1. This is how high-performance queues are built. Closely related is the Deque, short for double-ended queue. A Deque lets you add and remove from both the front and the back, all in O of 1. It is the Swiss Army knife of these structures, restricted to one end, and it behaves like a stack. Use one end to add and the other to remove, and it behaves like a queue. In fact, in real code, a Deque is often what you reach for to get either one. One important cousin breaks the fairness rule on purpose: the priority queue. Instead of first in, first out, the item with the highest priority always comes out next, no matter when it arrived, like an emergency room treating the most urgent patient first. A priority queue is usually backed by a structure called a heap, which keeps the top priority item ready in logarithmic time. That heap is a perfect topic for its own video. So here they are together. A stack uses one end for everything: last in, first out. A queue uses two ends, joining at the back and leaving from the front: first in, first out. That single difference, one end versus two, is the whole distinction, and it decides which problems each one solves. The costs are wonderfully simple. For a stack, push, pop, and peek are all O of 1. For a queue built the right way, a linked list or a circular buffer, Enqueue, Deque, and peek are all O of 1 too. The only slow operation is searching for or reaching some item in the middle, which is O of n, but that is not what these structures are for. Their whole point is fast access at the ends. Choosing between them is about order. Reach for a stack when the most recent item should be handled first, reversing things, undo, backtracking out of a dead end, or depth-first exploration. Reach for a queue when items must be handled in the order they arrived, task and job scheduling, sharing a resource fairly, or breadth-first exploration. Stack means newest first, queue means oldest first. In code, both languages give you these for free. In Java, the recommended tool for both is Dequeue. Push and pop for a stack, offer and poll for a queue, and prefer it over the old legacy stack class. In Python, a plain list works perfectly as a stack with append and pop. But for a queue, do not remove from the front of a list because that is O of n. Instead, use collections.deque with append to enqueue and pop left to deque, both O of 1. So to summarize, a stack is last in, first out, push, pop, and peek, all at one end, all O of 1. A queue is first in, first out, enqueue at the back, deque at the front, also O of 1 when backed by a linked list or a circular buffer. A plain array makes a fine stack but a slow queue. A deque works at both ends and can stand in for either, and a priority queue serves the most important item first, powered by a heap. Choose a stack for newest first and a queue for oldest first. If this helped it click, please subscribe for more visual explanations. And here is where you come in. Comment the data structure or algorithm you would most like to see explained next, and your suggestion could become our next video.